All right, hopefully everybody is back and settled from your coffee break. Things are going at a good pace, I think. You guys, everybody is in for a treat here. Next up is Dick Krieger. He is a member of our education team. Uh, when it comes to electrical, he's my go-to guy. Anytime I have a question, there's probably a few people I know who know more about electrical than Dick. Today, he is going to take you down a path talking about relays, which you may think you know things about relay, but you're going to leave here knowing a lot more about relays. So take it away, Dick.
Thanks, Jimmy.
And you can share now.
Okay, thank you. Are you able to see my PowerPoint?
Yes.
Great. On behalf of the Claysons at Dactic and ConsuLab, our education team and the entire group, I would like to thank you for inviting us and me to be here today. I'm going to talk about a subject that I've done around the country, and I've included some of the newest of relay technologies. And one of the first things I see when I'm standing in front of an audience is the look on their faces when I see relays. And that primarily is, oh man, another boring class. I certainly hope that isn't the case today. And I would ask you, if you're at all feeling like you learned something today, indicate so in the Q&A towards the end of the session, and I would appreciate hearing from you. Obviously, if you have questions during the presentation, please don't hesitate to ask them in the Q&A. We are monitoring your comments, and we can answer your questions. So let me try to get this thing working. There we go. There is an available resource for you on our website. The name of the resource right now is called Educational Diagnostic Strategies for Today's Vehicles. It's a 68-page handout. It covers relays, test lights, voltage drop, parasitic draw, testing current cross fuses, and specialized test equipment. It also has 8 pages of video and article references and hot links. So anything you see in blue, you or your students can click on them and be taken directly to that resource. I've previewed all of them. They're very valuable in learning this information. However, this handout does not include the latest, newest additions to the class on relays. And I promise you that that will come shortly. So I don't know why I'm having difficulties here with my PowerPoint. There it is. So there is a new relay class handout just for the relay class today. It's not done yet. It will be soon. And I will get a hold of Dactic, and they will make that available to you. And it'll also be on our website. Be honest now. Are you comfortable with your current knowledge of operation, testing, and diagnosis of relays today? I suspect most of you would answer yes to that question. Krieger, are you kidding me? It's a relay. What's to know? For the hands-on portion of today's class, I'm going to be using our newest lighting trainer, and I wish it was called Lighting and Basic Electrical Trainer. It's brand new. It's been out about, I think, 3 or 4 months. That's going to be demonstrated with a camera for our hands-on work. The front panel, and those of you that may have some of our lighting trainers, you'll notice some differences. The differences is the same incandescent lights for headlights and side marker lights are there. However, we've added LEDs for the park and turn And we have now 2 relays that are wired by students, and these are ISO 5-pin, very common relays for the top panel. And then what's new feature is all of the wiring sockets are 4 millimeter, and if you try to put a multimeter lead in there, they're only 2 millimeters, and they kind of flop around inside. You can't get a good connection. So on critical test points, we now add 2 millimeter test points that your meter leads will fit securely into and stay there. And that's a nice feature. The middle panel is new, and we have LEDs for the indicators. We have 2 more relays. So now we have a total of 4 relays. Relay 4 is a little special. I'll talk about that in a second. We have an ignition switch, a hazard switch. We have a multi-function switch. And I want you to notice the junction block where students will be making all of their wirings. All of the wiring receptacles are not red or black. They are yellow. The reason they're yellow is with this particular multifunction switch, you can hook up a ground switched or a power switched lighting system. The switch is capable for either one. We have a turn signal flasher, electronic. We have hazard flashers, electronic. We have a brake switch, a backup light switch. We have a horn, and we have a circuit breaker for the horn, because one of the faults for this trainer is to have a short from B+ to ground, which of course would let the smoke out, but now we have a circuit breaker that would trip. We have a horn button. We have a fuse box. And the newest features, the Relay 4 is removable, and it'll take a standard ISO 280 or micro relay, or it will also take the 1-inch square ice cube 5-pin relay. Why is that an advantage? Well, you can test circuits now from the relay socket, which you could not do before. And you'll see in my later presentation that relay testing at the socket, relay circuit testing at the socket is extremely important. You can also go into your desk drawer where you've probably got 3 or 4 defective relays, replace them, and add additional faults to the trainer for their diagnosis. The fault box has been replaced with an electronic one, so there's no more toggle switches. They are push buttons that are programmed by you, the instructor, with a programming key, so that your students cannot see what faults are pushed in or out. A little light comes on when you program it and then goes off when you remove the programming key. And that's a neat feature. The rear panel has, again, incandescent lights for the backup, the rear marker lights, and the license plate light. And we wanted those to be incandescent so you can use those for series and parallel and combination series parallel Ohm's law circuit experiments. And then the LEDs are the brake lights and the combination tail turn lights. This new trainer has all of the curriculum, all of the student-led curriculum written at 3 separate competency levels. So now you have a student who has no experience whatsoever. He is given a certain set of assignments that are written at his level, then maybe a student with some experience that you've had, and then the highest level of experience. So there are, all of the experiments, again, are written at 3 different competency levels. The curriculum covers vehicle lighting systems, Ohm's law, relays, lots of optional circuits. They will construct alarm circuits, They will do police lighting circuits. They will do headlight left on warning circuits. Quite a bit of instruction. 100 hours easily, depending on your style, is available with this trainer. And the neat thing about this new product is we are now using OEM type wiring diagrams for the middle and high level of experience. In the old trainers, we had a red wire from here to here. On the new trainer now, we have OEM diagrams that they have to learn to read and interpret. It's a nice change. There's 600 pages of curriculum, including instructor answer keys and tests. It is a complete educational package. Ready to go. Okay, relays, teaching and learning relays. Operation and testing and types. Relays, we're going to talk about common relays, PCB relays, bistable relays, new designs of those, and variations of. If you haven't heard the term bistable relays, you soon will. They've been used on cars since about 2008, and they're becoming very, very popular and common, and they're very different than what you're used to. We will discuss how relays are tested, and I submit most relays are tested incorrectly. You'll see why. And then relay circuit testing, which is often ignored during diagnosis. I'm sure most of you will raise your hand if we were in a room and I asked the question, how many of you have tested a relay? And you would raise your hand and I'd say, how did you do it? Most would take a ground source and a B+ source, touch the two terminals of the coil, and you're expecting it to click. Well, with today's relays, you've got a 50% chance of destroying that relay, and you would not know it. Relays are high current passing switches that are controlled by a low current circuit. No external movement is available. This is a quick review of relays for you and your students. A solenoid and a relay have things in common, but they are very different. They both have a coil of wire that develops a magnetic field. They both have a plunger that when the coil is energized, that plunger moves in one direction or the other. The difference between a solenoid and a relay is the solenoid has an external movement of the plunger that we use that movement for something, and a relay does not. So in this case, the plunger comes out of the starter solenoid, attaches to a lever that is in a pivot, and that lever is used to push out the starter bendix, engaging the flywheel and causing the starter to operate. So solenoids have external movement, relays do not. So what have you been calling this all of the years that you've been seeing this? Most people would call that a starter solenoid for a Ford, but it's of course used for many other cars. That is not technically correct. It is a relay, and Ford calls it a relay in their service information. If you went into an auto parts store and asked for a Ford relay when you wanted the solenoid, quote unquote, you probably would not get that part. But technically, if you want to get into detail, it is a relay. A relay has two halves or circuits. We have one half coming in from B+ to terminal 30, comes out of the relay on terminal 87, goes to some device, be it a motor, a light, a fuel pump, wiper motor, whatever, and then to ground. And when the relay is turned on, those contacts are closed and we have high current flowing between 30 and 87. This is called the high current controlled device or control circuit, controlled circuit. The other half of the relay comes from B+, goes through a coil, then goes to a switch, and then to ground. Now you might be saying, wait a minute, that switch can be on the positive side, and you're exactly correct. It can be either a ground switched relay or a power switched relay. And one of my cautions before you start jabbing test lights and jumpers into relay socket circuits, make sure you know what you're dealing with. So this is the low current device that when energized turns on 30 and 87. And by the way, 30 doesn't always come from B+. GM loves to take 30 to the device they're controlling, especially a fuel pump, and 87 is now going to B+. So you got to be sure that you know the wiring schematic for the circuit you're dealing with. And we have the low current control circuit. This one happens to be ground switched, but don't assume. Always check vehicle specific surface information. How many terminals can there be on a relay? There can be 3. And on this one, we have a set of contacts that are normally open. And we have a coil circuit that shares in common B+ feed to the coil and to 1/2 of the contacts. And then the third terminal is the coil ground that goes to a switch. We can have 4 terminals. And the 4 terminals are the common normally open contacts, and they're normally open but closes when the relay is energized. And then the other 2 are the coil circuit. And now we have 5 terminals, and all we did was add another terminal on that wiper there, and that is a normally closed set of contacts when the relay is off. And then when the relay is energized, we open that set of contacts and close the normally open set of contacts, energizing a circuit. These are called flip-flop relays or make and break relays. They're very common on cars. What you have to remember is these relays, you can have a 5-terminal relay where the 5th terminal is not used, but the relay is still installed in the car. So we'll talk about that a little bit later. So normally open and normally closed contacts, and those conditions are reversed when the relay is energized. What do they look like? That's the old member 3-terminal horn relay that was used by everybody for years. I've seen them on a few cars, especially trucks with a lot of add-on stuff with circuits and systems have been added. This is the very common ISO relay, 4-terminal. This is the same relay with the 5th terminal, and the 5th terminal again is 87A. If you look close right there, you can see 87A. Now that's important to remember, because if you're swapping relays and you're for diagnostic purposes, you can swap a 4-pin into a 5-pin socket if 87A is not used. It's kind of a little diagnostic trick there you can remember. So when you're swapping them, even though that 87A isn't used, you can use a 4-pin relay and have it work just fine. Relay terminal identification. We probably know this. 85 and 86 are the coil circuits, the low current device. 85 is normally ground, but again, GM, Ford, FCA, and many European and Asian vehicles are not on the same page. So you want to make sure that 85 is ground on the circuit you're working on. It may not be. 30 is normally used for B+, although as I said, there are variances or differences. 87 normally goes to the control device. And then 87A is normally not used, but it could be depending on the circuit that you have. Again, 30 and 87A are normally closed when the relay is off. 30 and 87A are open when the relay is on. 30 and 87 are normally open when the relay is off. And they are closed when the relay is on. As relays get smaller in size, now we call them mini or micro relays or micro 280s. And we'll talk about those in a bit. They don't have room anymore to put all those numbers on, so they abbreviate it and use 1 for 85. They use 5 for 87. They use 2 for 86. They use 4 for 87A, and they use 3 for 30. I know you've seen those relays. That's what they look like. There is a 5-pin ISO micro relay that has numbers on the terminals or the wiring schematic instead of the 3087 that you're used to. The different relay types that there are today. The standard ones, which is now the old style, were called ice cube relays because of their squareness, and they were about 1 inch square. They took up a lot of space, but they worked very well. Well, now with so many more circuits and so much concern with space, you're finding these to become more and more rare. Only in cases where there is a very high amperage circuit do you see these used much anymore. There's still a lot of them out there, but they've gotten smaller. Here is a simplified schematic for you and your students between a 4 and a 5-pin standard ice cube relay. You notice the only difference is the addition of that 87A, normally closed set of contacts. Everything else is the same. So, relay schematics that you'd see in a wiring diagram. Here is a 4-pin ISO relay. It's called, very common, it's to make and break. It either makes a circuit or breaks a circuit. Here is a 5-pin relay with the addition of 87A that we've seen. And again, to repeat, that's exactly what it does. It takes that 87A, opens the contact, and closes 87 when the relay is energized. The first new thing that you may have not heard of is this one. Notice the schematic says 87 and 87B. And notice that the wiper now turns on both 87 and 87B when the relay is energized. This is a Bosch relay. It turns on 2 different circuits at the same time. It's very common in BMWs and Mercedes and some Volkswagens. It's a German circuit design, but it looks totally identical to any other relay except it says 87B instead of 87A. Now you can interchange this with a 5-pin ISO 87A relay. You see you can get into all kinds of problems. So there's your first new item today, is that rare German relay. Here's one that you may or may not have seen before. They are used quite commonly on RV, marine, boats, trailers, campers, or cars that have had a lot of things added onto them, mega bass stereos or whatever. It's a relay with a replaceable fuse built into the relay. Again, they're normally found in aftermarket applications and those other systems. This is what it looks like. It's a relay with a fuse right on side of the relay. It's an ATC, common ATO fuse, and you can get different amperages. The contacts are always rated for 30 amps, but you can have a less amp fuse in there for smaller circuits. And of course, we should be now recognizing that schematic as showing a diode in the relay, which we know that there is a diode across the coil for spike suppression, which we'll chat in a minute about. These relays, if they have a diode in them, are polarity sensitive. If you hook one of these up backwards, not knowing 86 and 85 positive or ground, you can destroy the diode, but the relay will still work. And we'll talk about and show you that a little bit later on. Diodes are not as common as they used to be, but they are still used. Make sure that you don't believe that there's no more diodes anymore. There are. And then the common one used today shows a resistor across the coil. And these are not polarity sensitive. Either 85 or 86 can be ground or B+. The resistor is not as good at blocking suppression or as suppression spike control as a diode is, but they're used. What is spike? Coil spike? Anytime you have current flowing in a coil and then you stop that current, you induce a voltage greater than the supply voltage, and that is called induction. That's how an ignition coil works, by the way, step-up transformer. If we allowed that voltage to escape into the circuit, we could damage computers or sensitive electronic components. So we got to control that spike and keep it in the relay. It's called the inductive kick, and it can be 200 to 400 volts. Have you ever measured that? Have you ever somehow measured the inductive kick of a relay? I'll show you how to do that. Here are 3 relays, 2 of them with resistors as a coil suppression, and then the one on the left is a diode. So ISO relays still have diodes in them. There are 2 types of coil spike suppression, as I said. One is a diode, and one is the resistor. Now, most of these diodes are replaceable. If you're like me and cheap, you open up the relay, find the blown diode, unsolder it, and put in a new one, which is a 1004 diode. You used to go to Radio Shack to get them. Now you can get them from Mauser, DigiKey, any number of places. They're about like 7 cents a piece, so they're very cheap. Here I hooked up my Pico to a normal coil on a relay, and I'm on the 50 volt range, and I shut off the relay and captured the spike, and it spiked to 25 volts, which is pretty normal. This was a resistor suppressed diode in good resistor suppressed relay in good condition. 25 volts the system can handle. Now here I've connected it to a diode suppressed relay with a blown diode. I switched my scope to a 500 volt range, and I have a 280 volt spike going out into that circuit, touching PCM modules, whatever it's connected to. And this was a diode suppressed relay with an open diode created by wrong bench testing. The mini relay is a little bit smaller. Again, it is identical to the big ice cube relays. It's just smaller in size. And now the micro or 280s. These are numbered relays again, and we have a 4-pin and we have a 5-pin, identical internal operation, just physically smaller. And you see the only difference between them is terminal number 4, which is 87A. This one is a resistor suppressed diode, a resistor suppressed coil, and this one is a diode suppressed coil. So they still make diodes. This is a 4-pin micro or 280 relay. Notice when you turn it over, you have pins at each corner. If you have that relay, and these are extremely common in today's vehicles, you know exactly for sure that the 2 common terminals of the coil are going to be, this is a resistor suppressed diode. There's 86 and there's 85. Why does it have to be that way? It's very simple, because that relay can be taken out and plugged back in another opposite direction. Therefore, it has to be resistor suppressed, and the 2 corner diagonal terminals are 85 and 86. That means the other 2 diagonal terminals are 30 and 87. And if you have 5 pins on it, like this one over here, the middle one then would be 87A. ISO relay variations. Now we have the 280 micro on the left and the full-size 5-pin ISO on the right. These 2 relays are identical, and the only thing different about them is the size. So on our trainer, either one of those relays will fit into that socket. There's no fuse box restrictions, so either one of those relays can be used on the trainer for additional diagnosis.
Dick,
Yes.
Real quick.
we have 2 questions.
Certainly.
Now is, I think, a pretty good time. One of them is, I didn't catch the 2 online suppliers that you mentioned about purchasing diodes. Could you repeat that?
Yes, that is in the handout. Mouser, M-O-U-S-E-R, Mouser.com or Mouser Electronics, and DigiKey, D-I-G-I-K-E-Y.
Okay, and then the second question is there a specific name for the relay which has the external use fuse?
I've heard it called auxiliary relay with a fuse or fused relay. You can Google fused relay and you'll get all kinds of different sources for those. And later on, we'll show you, if you want a socket, instead of trying to hook up a bunch of alligator clips to all of these relay terminals, you can get relay sockets for 4 and 5-pin relays for like $1.50 a piece. They're very inexpensive. Okay, so moving on, now we've changed the configuration a little bit. The one on the right is the older style and the one on the left is the newer style. They are not interchangeable, but inside they operate identically. It's just a different configuration of the terminals. Now, remember that not all automotive and truck relays are ISO. ISO stands for International Standards Organization. And not all relays are following that, so they can be totally different. And these are relays, other than the one on the left there, taken from different vehicles. So how do you know where the terminals go? You look at a wiring diagram. You must identify those terminals before you test anything on those relays. A vehicle-specific wiring diagram. The newest relays today, or some of the newest ones, are called solid-state relays. They're not really new. When your students put in that 5,000 watt mega base in stereo in their car, they probably had a high-powered amp or power relay, which was electronic in nature. They can be attached to a circuit board or fuse box called PCB. PCB stands for Printed Circuit Board Relay. The important thing to remember about these are they do not click. So a normal relay that's working just fine does not click anymore. What are solid state relays? For those of you that are high-level electronics guys, they're MOSFETs, metal oxide semiconductor field effect transistor. Say that 15 times fast. The advantages of a solid state relay are many. Silent, no more contact arcing issues. They can support pulse width modulation circuits. There are no more voltage spikes. They can be used to control voltages. So example, they're so fast in their switching that we can use them in place of a resistor. So many daytime running lights or fuel pumps or many blower motors and so on are now controlled with solid state relays, and we control the speed by pulse width modulation, how fast and how long we turn them on and off in milliseconds. And because we are monitoring the current by the switching speed, we no longer need fuses or circuit breakers. So we can protect the circuit without a fuse or circuit breaker, and many cars are using solid state relays in that way. Anything we can do to save money. The disadvantages, they are more costly and they can be difficult to diagnose, and they are non-serviceable. How do you test them? Normally, solid state relays have to be tested with scan tool bidirectional control. Now, depending on the vehicle, if you have a global platform scan tool, GM gives you the capability of controlling a lot of bidirectional relays. So you can control solid state relays with your scan tool. Vehicle specific scan tools are the best, but again, as teachers, we don't always have that kind of money. Some will allow you to do that and some won't. It depends on the vehicle. If you took the covers off of a solid state and a mechanical relay, you would see the coil, you would see springs, you would see the armature, the contacts, and the terminal. If you took the cover off of an electronic solid state relay, all you see is the circuit board. No click. Integral relays. The 2009 Ford Focus has something called a smart junction box. I question the word smart, but that's okay. The horn relay, as you see in the wiring diagram, is non-serviceable. Here's the part many of you know and love, TIPM, Totally Integrated Power Module for Chrysler corporations. Chrysler FCA has had huge problems with their TIPMs, especially with the fuel pump relay. TIPMs were replaced quite commonly. They're not cheap. And you notice that all of those relays are non-serviceable. There's a Ford Smart Junction box, about $205 plus programming charges, just because one relay was bad. Here's a TIPM, $300 plus programming charges. Now notice that this also has removable relays and fuses in it, but the solid state relays are down inside where you can't get to them. Dorman is now remanufacturing these parts and are now available in AutoZone and aftermarket O'Reilly's and so on. You don't always have to go back to the dealer. There are repair kits to replace a relay on a TIPM if you want to. If you're comfortable with soldering and desoldering small terminals, you can repair these yourself. This is a product we took off of a 2012 GMC pickup. And here you see that's called the Power Distribution Center, or PDC. You've seen dozens of these if you work on cars. Here you see removable relays. There's some ice cubes in there. There's some micros in there. There's some minis in there. All the reds are removable relays. And all of those green arrows are the things that we know and love called cartridge fuses that give us trouble when we try to test them. And then the yellow are all of the mini, micro, space-saving ATO, ATC fuses that you simply unplug. But inside of that, which I took apart, and the only way I could get it apart was to take a die grinder and slice all the way around the two halves, because they don't want you opening up this part. There are all of the PCB relays for that truck. And this is 2012 now. This is not a new vehicle, 8 years old. Those relays are all non-serviceable unless you want to go through the soldering process and cut that thing apart. And GM calls them PCB integral relays. As I said, you can go online and get replacement relays, but it's not easy or fun to replace them. Here is the TIP'em, FCA TIP'em. There's a website there that's also in your handout where you can go and get remanufactured TIP'ems. What they actually do is the fuel pump relay on these Chryslers were horribly troublesome. So they've designed a new relay with heavier duty contacts that fits in the same size of location number 1 right there is the fuel pump relay. So it's a retro kit. And many of you know that if you work on Chryslers, there's also a repair kit available where you cut the wires to the TIP'em and mount a separate relay outside of the TIP'em. That can be done also. Here's something kind of new. The one on the left is a standard ISO 5-pin. The one on the right is new solid state relay. GM was the first to start using these. Notice what's different. You got 3 pins on one side, 3 pins here, but you got a pin in the middle and no pin in the middle here. The reason they did that is so you cannot physically install this relay in that socket. In 2005 and newer, GM has used these. Here's a wiring diagram, and I don't expect you to read all of it, but you see it says high beam PCB relay. And if you look down at the legend, you also see that fog lamps, high beam headlights, horn, and ignition are all PCB relays. They are replaceable. This relay, although GM uses the same acronym, these relays are replaceable. This one was taken off a 2006 Grand Prix with a lighting option, so the high beam headlights are controlled with a solid state relay. But you notice that the manual shows a coil, a resistor, and contacts. And they do that so you basically can understand how it works, but you cannot control the coil circuit like you would on a mechanical relay. You have to be careful. Again, that's what it looks like. These are replaceable PCB relays. Now, the confusing part is we have the same acronym used in 2 different applications. So at first we said PCB relays were soldered or mounted on a circuit board and were non-serviceable. It changed the whole part. Then GM comes along and says, well, we're going to call our PCB relay replaceable, and it is serviceable. So don't, or you and your students get confused on that because of the term PCB. It doesn't always mean the same thing. Here is a standard 5-pin ISO mechanical relay with a cover off. Here is a 4-pin ISO micro relay with a cover off. No coil, no contacts, just a big IC chip. This is one where the chip was literally blown off the circuit board. It had a PCM issue with a stuck-on driver. And replacing the relay would have not fixed that problem because it was improperly diagnosed. In other words, the PCM was commanding that relay to stay on all the time. And it just wasn't designed to do that. So it decided to give up its ghost and blow the chip off. Remember, solid state relays do not click. More new relays. Bistable. Bistable relays are not new. They've been used in RC controlled model airplanes, boats, cars. They're used in industry. They're used on machines, presses, assembly line machines. And now recently we've started using them on cars. Say what? Bistable relays. 2013, GM started using them on their battery saver system. The relay on service information can be called battery saver, auxiliary power, or accessory power relay. This is what it looks like. It's replaceable. For now, GM uses a relay that is green in color. It can have 1 or 2 coils inside, but I use the word coils because most of the bistable relays that I've seen are not mechanical relays. They're all solid state. The difference is once a bistable relay circuit is energized, the relay stays in whatever position it was commanded, on or off, even though the coil circuit is turned off. So the coil command is momentary and it shuts off, but the relay doesn't. The relay stays where it was told to be. In order to change the relay status, another circuit has to be energized to switch the relay back to its previous condition. There is no current flow in the coil circuit once that momentary circuit is activated. Bistable relays. If I had all of you in the room looking out over, I'd say, how many of you have heard of a bistable relay? I'm sure there'd be some of you that would raise your hand. For explanation purposes, I've created this diagram. It is not representative of what's in the relay. As I said, most are solid state. But if you want to understand how it works, you've got 2 coils on this relay. You've got a common armature that runs through both coils. And both coils share a common ground. Then we have a set of contacts that the armature either closes or opens, but there's no spring to return them back. It stays wherever it's moved to. So we have one coil connected to one circuit that either turns it on or turns it off. And then we have another coil connected to another circuit that reverses that position. Again, these are momentary coil circuits, just on for a short millisecond or 2. Most are operated by modules, quad driver, or CAN, not mechanical switches anymore. There is a 1 coil bistable that's very rare. I've never seen one. I've seen a picture of it, but they have 1 coil. So there's the B plus coming in. There's the B plus going out to whatever circuits we want to control with this relay. And then we have coil polarity one way to turn it one way, and then we reverse the coil polarity to move it the other way. Again, these are extremely rare. I've never seen one. Most are the other type that we've discussed. There is what happens if you take the cover off of the GM bistable relay. I bought some from China. The dealer gets 40 bucks a piece for them. I got $8 a piece for them, and they shipped them from China for me in 2 weeks. It was phenomenal. So I deliberately took the cover off. You can see I cracked it a little bit, but I was expecting to see some mechanical components, but what I saw is another relay. So we know that this relay is solid state. The relay underneath is a Panasonic relay, but they covered up with their GM branding and cover. So it's a solid state design. What do we use a bistable relay for? Who uses them? GM, BMW, Hyundai, Kia, and many others now use bistables. Here is a 2018 Buick Regal battery saver system. Well, what is a battery saver system? You know that one of the biggest plagues of dealerships and transportation of vehicles over long distances is the batteries going dead. So this system has a circuit in it that literally disconnects most all circuits from the car so the CAN bus doesn't stay awake and draw the battery down. So you got to be able to know how to energize that battery saver system and de-energize it. Many people that are driving these cars don't even know they have that feature in their car. I hope you can see the diagram. I couldn't blow it up any bigger, but in the middle there in the circle, it says battery saver relay. And you notice it's got 5 terminals. So we run power through a power supply transformer. And we want that transformer to get a nice clean 12 volt DC from the battery, but it goes through a transformer, modulates it, so the battery, if it goes a little bit down, the inverter will still maintain that voltage. And that B plus is waiting right here at that terminal. Now we have the body control module that can turn on this purple circuit, which is attached to one of the coils. And the coil you see shares a ground. The BCM can also turn on the gray circuit, which is connected to the other coil. And again, they share a common ground. Now, again, there are not coils in this relay. There are electronics. But for the purpose of explanation and understanding, both GM and me draws them that way. When the relay is turned on, we connect 5 main fuses that goes off and does many different things in the car. Again, 2 coils, quote unquote. Coil command is momentary, and the relay stays in that last commanded position. This is a excerpt from the Buick service manual. I know you can't read it, but basically it says to turn this system on, turn on the hazard flashers, apply the brake pedal, then turn the ignition key to start or push the ready button while your foot is on the brake pedal for longer than 15 seconds. And that will turn this system on and shut down everything that was drawing your battery down. You want to turn it back on again. The car has come across the pond from where it was built in Europe or Asia, and they want to energize it. They are doing this as they unload that car from the boat or from the truck or wherever. And dealers use this on their lots. Also prevents theft. Here's a close-up of that previous schematic that you saw. It turns on 1, 2, 3, 4, 5 fuses. And there's the relay. This is what it looks like. Again, the GM OEM part is green. Hella also makes one, but it's identical relay, but it's not a green color. Hyundai, Kia, BMW, and others are using bistables. not necessarily for battery saver circuits, but for many other circuits. Mitchell draws their schematic using old style contacts and coils. This is the same car that we just saw, the Buick. Notice it comes from the power supply transformer, but it has not got coils or contacts inside. But that's how they draw it, so you'll either understand it. But don't make the mistake of start attaching 12 volts with a test light to these things, because you're not going to have good result. This is a standard relay, side view and top view. This is the GM bistable relay. Notice they call it latching. Latching relays stay where they were commanded to stay. The GM part number, those of you that want to write it down, is 135001116. That'll get you this green relay. You can Google that and get all kinds of information on it. This is a picture of that relay installed in a GM car. Next to it is a GM relay micro 280 that is not a bistable relay. Now, those of you that are thinking, is there a problem here? There's a socket of a relay that is not installed. So, the standard ISO 280 is on the left. The GM bistable is on the right. What could possibly go wrong? Could you see a problem if a student or a technician or me or you wrongly interchanges a standard for a bistable? The answer is yes. Why didn't GM think about that? I don't know. In addition to latching relays, you can have latching relay circuits that uses a standard non-latching ISO relay and makes it into a stay put relay once its coil is commanded. Now, a latching circuit uses switches, diodes, or multiple relays to create the specific application. They're used in aftermarket, add-on security, lighting, entertainment systems, and they can be created with standard ISO relays and switches. This is just one example of one of the multiple assignments that are in the handout that is currently available for you, that you can have your students wire up relay latched circuits. In this case, all we need is a standard 5-pin relay and a normally closed and a normally open push button. Again, they're available from Mauser. They're about $1.50 a piece. They love to do this. They like to build bench circuits, as you know. These make great student bench projects. Builds interest. Again, the handout has several of these circuits built into them for your use. GM high power relay, old and new version. Say what? Again, I would ask the audience, how many of you have heard of GM high power relays? There are two types of GM high powered relays. GM was having a historical problem with the fuel pump relays and some of the wiper motor and blower motor relays burning out. And so they wanted to design a relay that would take up the same space but handle more current, so that you know that it would be more robust contact surfaces and materials. So now we have two types of GM high power relays, and it's important for you to know the difference, and I'll explain why shortly. This is not in your existing handout, nor our bistables, but it will be in the new handout. Notice that the common one is on the left. It says high power on it. There's the part number for it from GM. The resistance spec for the coil is 80 ohms. That's right in the middle of the ballpark for all ISO relays, isn't it? And the coil current is about 160 milliamps. That's normal. On the new design, the coil resistance is higher than most all others. It handles higher amounts of current with lower control current by the PCM BCM. So the less current we have going through that module, the better it likes it. So the high power new style has 210 ohms of resistance in the coil, and it only draws 60 milliamps. Now, you want to be careful here, because if you have an older style high power relay that draws 160 amps and you throw it in a circuit that's only supposed to handle 60, there might be a problem. Burning out PCMs today is not nearly as common as it used to be because of overcurrent protection and shunting fuses or shunting resistors inside the PCM. It's not, I mean, it still can be done, don't get me wrong, but it's not as common as it used to be. So here I am with that style of relay with my trusty fluke measuring the coil resistance. You notice it's opposite corners, and it's 82.9 ohms. These are the high rated contacts, but the standard coil resistance. Here's the new version measuring 219.5 ohms, which means lower coil current. So now you've learned about bistables and GM high power relays. Are there any questions on relay types so far? And then we'll move into diagnosis and testing.
Dick, you had one question, which I think you answered, but maybe you want to re-answer it. And it says, what is the level of the current or amps for these relays?
On the bistable relays, they're in milliamps, very, very small. On any ISO standard relay, most of them are max rated at 30 to 35 amps. Using Ohm's law, you can easily calculate the coil current by taking your system running voltage, 14.5, and your 80 ohms of static resistance and figure out the coil current. So, but as far as, unless you've got a real heavy duty power relay, most of them are maxed at 35 to 40 amps on an ISO relay. There are two types of testing of relays. In or out of the circuit, we call static, and that's where you make the relay go click, click. Most of you have done that, but have you done a dynamic testing of the relay? And I suspect that some of you have not. Dynamic testing in the circuit. This is something that is very often overlooked. And now testing the circuit at the socket with the relay removed. And we're not going to even test the relay. We can do that on the bench. But what about the circuit? And then I'll talk briefly about specialized equipment available for testing relays and relay circuits. Warning, warning, warning. You need vehicle-specific service information for proper diagnosis. Do not assume that all relays are the same because they look identical, but they're not. How do you tell if a relay has a suppression diode inside or not? If I was to throw that open to the audience, how would I get an answer? How do you tell? You got a relay, you don't have a schematic, you don't have a wiring diagram, and you want to know if it has a diode inside or not. Well, one answer is you could pry the top off of it, I guess, and look for a resistor or a diode. How about this one? Could you use an ohm meter to tell? You know that if a diode is hooked up to an ohm meter and you reverse the leads of the ohm meter, the diode will give you two different resistance readings. Would that work in a relay? Could you use the diode test function of your digital multimeter? We know that the diode test function puts a little bit higher voltage through the relay and gives you the voltage drop and tells you if the diode is good or not. And by the way, the answer to both 1 and 2 is no, you cannot do that. I will explain why in a moment. Could you use a 12-volt test light to determine if the relay has a diode in it? And the answer is yes. Can you use vehicle-specific information? Yes, you can. The reason, how do I get rid of this? Guess I can't. Okay. The reason you can't use an ohm meter is because the diode is connected in parallel with the coil, and the diode has much higher resistance than the coil does. So even if you do hook up your ohm meter and reverse the leads, the ohm meter will read 80 ohms or the resistance of the coil each way. Even if the diode is there, the only way it would read different is if the diode was completely shorted as a conductor. Then the ohm meter would read 0. Testing a relay, get in trouble here. Guess I can't. Oh, there we go. Thank you. Testing a relay with a diode in it, or to determine if the relay has a good diode in it. I'm sorry for the text, but here's what we're going to do. We have to accurately identify pins 85 and 86. Wiring schematic, or look on the relay itself. Some have markings on them. You need a 12-volt power source and ground. I like to use a 194 bulb. That's the common bayonet bulb that plugs into marker lights and so on. Or you can use a 12-volt test light. However, do not use a computer-safe test light. You're looking for about 250 milliamp draw of your test light or your 194 bulb. That will not hurt the relay. It won't hurt a computer circuit. The 194 bulb makes an excellent relay testing tool. You connect the test light or the 194 bulb from B+ to one of the 85 or 86 terminals. Don't care which one. And you connect ground to the other one. So you've got B+ through a bulb to 85 or 86, and then you've got the other 85 or 86 going to ground. Now, those of you that are sharp, what'll happen? If the test light comes on dim and the relay clicks, the following is true. The relay has a resistor inside or a diode inside. So now it could be either or. And you have connected the test light in series with the coil, but the current is still enough to energize the relay coil. So we still don't know whether it's a resistor or a diode, but we do know that the coil has a continuous continuity circuit and the relay clicks. We're not done. Now reverse the polarity of the test light or bulb on the opposite 85 or 86 that you were the first time. If the test light comes on again dim and the relay clicks, the relay has a resistor in it and it is good. Or if there's supposed to be a diode inside, the diode is blown and the relay will operate completely normally in the circuit without spike suppression. I'll back up here in just a second. If the test light comes on at full brilliance and the relay does not click, you have a diode inside and it is good. I'm going to demonstrate this so you can see how all this fits together. To do that, I'm going to turn on my camera. Hopefully you can see a little bit dim, but right here is a 194 bulb. It's got two leads on it. One is connected to B+, and the other I've got to a probe. Here is my ground, and if I touch the probe to the ground, the bulb comes on. Now I'm going to take a relay, 5-pin ISO relay, and I'm going to connect one of my grounds or powers to one side of the relay circuit, and I'm going to connect it to the other. The light came on dim and the relay clicks. Can you hear the clicking? Now I'm going to reverse that and do the same thing. The bulb is coming on dim and the relay is clicking. So what does that mean? That means that there's a resistor suppressing this relay coil and it's good, or there's a diode that was supposed to be in there and it's bad. And I look on the side of the relay, it shows a resistor in there, so I know this relay is good. Now I'm going to take another one and I'm going to do the same thing. The light comes on at full brilliance. The relay did not click. Now I'm going to reverse it. The relay is clicking and the bulb is on dim. So this relay has a diode in it and the diode is good. Now, just to confirm, those of you that doubt you can't use an ohm meter to check for diodes, we know that this has a diode in it. So let me hook up my ohm meter to the two coil terminals. And the ohm meter is reading 82.8 ohms. Let me reverse it. (82.8), exactly the same reading. So you cannot use an ohm meter to determine if there's a diode in the relay. So that's how to tell, and that's how to test the diode. Now, if you simply hooked up 12 volts and ground to that relay coil and it had a diode, you would get a momentary little, the voltage or the current would go up, the diode would open up, and the relay would still function normally, even though you have no longer any spike suppression.
Dick?
Yes.
We have an interesting question that you might want to address.
Sure.
Won't the resistance of the test light, and hence voltage drop, reduce the current on some relays enough so that even though the relay coil may be partially energized, the magnetic field won't be strong enough to get the relay to click?
That's a good question. That's why I specified the 200 to 250 milliamps. With those specs, I have not seen that problem. And we're going to do voltage drops across contacts here, and I'll prove it to you. But to answer his question, I have not seen that in the 250 to 200 milliamp range of using a bulb or a test light. Now, I said don't use a computer safe test light. This is a computer safe test light by Mac, And when you hook it up to a circuit, either a green LED comes on or a red LED comes on. I checked the current draw of this thing. It draws 17 milliamps. And you can test all day long on a relay, and you will not get any energization whatsoever. You could use a headlight to do this with, but you don't want to, because that's probably going to cause some problems with too much current. The 200 to 250 milliamps is a good ballpark range. There's you can buy these sockets online for like 50 cents. They're not a lot of money. That's a 194 bulb and a socket. You can cut them out of an old car when your students take them apart. Okay, so that you don't see all this mess of wires that I have on the trainer, I have connected this circuit up. So I have this fuse right here at B+. It goes over here and feeds terminal 30 of relay 4. Another wire comes off of the same fuse and comes over here and feeds one terminal of the backup light switch. The other terminal of the backup light switch goes over here and feeds terminal 86 of the relay. The other 85 terminal of the relay coil goes over here to ground. Then the last wire is a red wire coming out of terminal 87 going up here to the parking light. And again, the parking light has to be grounded over here to ground. So when I turn that backup light switch on, I'm going to expect that backup or that marker light to come on if the relay is good and I wired up my circuit correctly. Then this we'll use for the demonstration, and all I've really done, everything down here is the same. The only thing I've done is have the relay now control the low beam headlight instead of the marker light. So that's what I've wired up here, even though the wires are all hard to see with you looking through a camera, but it's easier if you were standing in front of it. So there is the portion in that dotted white box. There's number 4 relay, and my next slide shows you a close-up of that. So there's the fuse, there's 87, there's 30, there's 87A, which is not used, there's 86 coil supply from the switch, and there's 85 going to ground. So that's a close-up of what circuit I'm going to be using here for testing. And you notice the relay has a piece of white tape on it with a C. That is removable, and we'll show you that in a second. Dynamic relay testing. This is something that a lot of technicians and instructors and students do not do. So we have a relay out of the circuit on a bench. We hook up a ground to 85. That's the coil ground. We hook up a test light to B+ and touch 86. We know that that coil will energize unless we've reversed polarity it because of a diode. If so, we'd switch our wires. But that will energize the relay coil. Now, through a fuse, we hook up B+ to 30. And then 87, we come out and go to a rated load and ground back to the battery. And now with a millivolt meter, we measure the voltage drop across 30 to 87. What is that telling us? It's telling us how much voltage is dropped across the two contacts inside the relay. Now we know that contacts over thousands of cycles can pit, corrode, overheat, and so on. But if you simply get a relay that clicks and put it back in the car, you do not know if it's good or not. You must check voltage drop across the contacts of the relay. You're measuring the voltage drop across 30 to 87. The best technicians do not rely only on resistance or test light testing of the relays. Voltage drop testing across terminals using a load measures the health of the relay contacts. Again, voltage drop testing across the relay contacts. Remember the term rated load. Demonstration. Okay, if I turn my switch on right now, my marker light comes on. There you are. Switch off, switch on. Now I'm going to take my voltmeter, set it up for millivolts, turn on the light so you can see it, and I'm going to measure the voltage drop between 30 and 87. And it says 7.5 millivolts. Would you call that a good or bad reading? The answer, of course, is that's a very good reading, because that 7.4 or 5 millivolts is an insignificant, negligible amount of voltage drop across the contacts. Can we assume the contacts are good? The answer is only if that relay controls one 194 bulb. Let's go back to the term rated load. When we're testing voltage drop of the contacts of the relay, we want the load going through the relay to be as close to the same load that it controls in the circuit. So watch my meter as I go up to change the 194 to the headlight. Now I have 93.4 millivolts, which is almost 1/10 of a volt. Now we know that from our experience in the past, we don't want any more than 200 millivolts across, voltage drop testing before there's a high resistance problem. So we're still good. But my point is, when you're doing this on the bench, make sure that the load you're putting through the relay matches the load in the circuit. How do you do that? You can do it with seal beam headlights. You can do it with any number of high amperage devices that you want to add in parallel until that relay is controlling the amount of current that it does in the circuit. And you'd be surprised that it'll pass a low current test, but a high current test. Now, this is a brand new relay, so it's okay. I wanted to make sure you understood that. A blower motor, case scenario, was running slow. They checked the open circuit voltage available at the motor, and it was 12.6. Yet the motor was still running slow. So they changed the motor, but it didn't fix the problem. Now, those of you that are sharp, and if we were in the classroom, I would ask, what's wrong with that diagnostic procedure? And you notice the words underlined are open circuit available voltage. And one of the things that I teach in my diagnostic classes is the worthless time and wasted effort that doing open circuit voltage is. If you had a dim headlight on your car and you unplug the plug and you hook ground to power, you're going to get 12.6 volts until you hook it back up again. So they made a mistake when they checked open circuit voltage. Then they did a voltage drop test across the relay contacts, and it showed 3.8 volts, 3.8 volts. That means that blower motor was running on less than 9 volts. The relay contacts are burned and pitted due to the previous shorted blower motor that was running slow, drawing excessive amps. The relay could still handle it, but the contacts got hot and pitted, and the voltage drop test revealed that problem. How many you think would miss that diagnosis? So don't assume that everything is okay just because you put a new part in. When you take a relay out of a socket, especially students, you have to mentally visualize what pin went where. So we grab the relay and we pull it out and we turn it over. So we know that 87 is now on the opposite end. 30 is there. It's where it belongs. 85 is on the opposite end. 86 is on the opposite end. And 30. So all I'm saying is here, make sure you mentally remember where these pins are when you take the relay out and turn over and look at it. Same thing is true on the old style 5-pin ISOs. Only here, you only have to remember 2, which is 86 and 85. The rest of them, you can't have them backwards. 87, 87A, and 30 are all the same. Dynamic testing in the circuit. Now we dynamic tested the relay. Now we're going to dynamic test the circuit. We got a fused jumper wire, and we've connected it after we looked at our wiring diagram between 30 and 87. As soon as we plug that in, what do we expect to happen? Remember, the relay is out of the circuit now, but we've connected a fused jumper wire between 30 and 87. What we expect to happen is whatever that relay is controlling should now be operating. And remember, we always want to check wiring diagrams first, and don't ever use this without a fuse. You want to let the smoke out of a computer, that's a good way to do it. Never assume that all relays are the same. In this case, I have connected an inductive ammeter, or I could put an ammeter in series with the jumper, it doesn't matter. And I'm now reading current flow. What does that current flow mean? What am I measuring? Well, if this relay was controlling a fuel pump, am I measuring the current flow of the fuel pump? Yes or no? And the answer is no. It is the current draw of the device circuit, not the device. So if we have problems with grounds, corroded connectors, or loose wires, frayed wires, anywhere from where the connection point between 30 and 87 is made at the relay, that reduction in current flow due to high resistance will be seen on the ammeter, but it is not the current flow of the device. Now, this is a good diagnostic test because if you suspected you've got a problem in the circuit before you've done any surgery at all through harnesses or laying on your back or whatever, you can take 2 wires, a positive and a ground, go back to the fuel pump or whatever you're checking, directly connect it to the terminals of the device, put your ammeter around there, and if you get a lower or higher amperage reading, you know somewhere in that circuit you've got a problem. Again, if the current is greater at the device than it was at the relay socket, something is reducing that current, and it could be in the positive side or it could be in the ground side. And of course, you can use voltage drop testing and circuit loading to find which one. Again, device circuit, not the device. Demonstration. I'm going to take the relay out. This is standard 5-pin 280. I have homemade a jumper with special configured pins that fits that socket. So I'm going to put it across here. And I'm going to move my leads down to operate the 194 bulb. I'm going to hook up my ammeter here. I forgot to do that. And I'm going to use that same inductive ammeter. I really like this tool because 2 reasons. Number 1, it's got clamps big enough to go around a battery cable. Number 2, it's inductive and it's accurate to 1 milliamp. So I use this for my parasitic load testing without having to disconnect any wires. So I'm going to go up here to milliamp, turn the light on, and turn the switch on. And I accidentally disconnected my feed to the relay. And here we go. And I hooked my ammeter around there. I'm not getting a good connection here. Pardon me just a second. There we go. And it shows 339 milliamps. I can't get the glare out of it, but trust me, it shows 339 milliamps. So that is the entire circuit that I'm reading to that bulb, which includes through the relay from B+, through the bulb, back to ground. Now, if I simply move those up to the headlight with the same jumper installed, you probably can't see that, I'm sorry. It says 4,213 milliamps, which means I'm reading about 4.2 amps to that headlight. So again, if you want to hook your ammeter in series, you can, or you can use an inductive meter.
Dick,
Yes.
somebody wants to know what size fuse do you have in your homemade jumper?
It's a good question. Let's see, 100 amp? No. When you buy a fuse jumper wire like this, you can get them at AutoZone. That's where I bought this one. It's got a standard HTO fuse in it. And that's the next slide in my PowerPoint tells you that when you check a circuit this way, don't use the 30 amp fuse that came with the jumper, because that's the max. That's what the 10 gauge wire is rated for, is 30 amps. So let's go back to the PowerPoint. I thought I had a slide in there about it. I do a little bit later on. The answer to his question is you want a fuse about 75% less than the circuit fuse. So if you've got a 20 amp circuit that you want to check the draw on with your jumper, I would put a 15 amp fuse in there. I don't want to go higher, I want to go lower, because most fuses are rated at about 75%. In other words, they'll take a 25% surge without blowing. So I know that the circuit draws less than 20 amps, so I'm going to put a 15 in there. 75% is a good ballpark.
Dick, brand,
Yes.
model of the meter.
My meter is a Fluke 87.
No,
Oh,
no, the
this.
inductive.
Okay, let me switch the camera back on here. I lost my cursor. There it is. This meter is made by ESI, Electronic Specialties Incorporated, It is the model ESI-688. I don't know if you can see it. There's it is, 688. It's about 200 bucks. You can get them online. You can get them from AES Wave. Maybe Dectic carries a line of electrical test equipment. I don't know. But ESI-688, and it's got a built-in multimeter at the bottom here with these two red and black leads. I never use it. I want my fluke. But I'll use this for amperage testing every time. Now, we're going to test the socket using a test light. So here's the circuit that we've hooked up, and you see that we have B plus connected to fuse 1 going to the switch, which then turns on 86. We have fuse 2 powering B plus to terminal 30. Now, in reality, fuse 2 would probably be higher than fuse 1. Then it comes out of 85 to ground. So this is a positive switched relay circuit. And then the load comes out of 87. The relay is removed. I connect a test light from ground to pin 86 of the socket. What will the test light do? It's going to do one of two things. It's going to be off or it's going to be on. If it's off, one of three things is happening. The switch is not turned on. Fuse 1 is blown, or there's a break in the circuit somewhere. So if I want to test the switching circuit of this relay circuit, I would simply turn the switch on. That test light should come on, telling me, yes, the switch is good, the wire is good, the fuse is good. Now I can voltage drop test that if I want to get detailed. But here I've tested the switching circuit of the relay at the socket. Now I'm going to connect the test light to terminal 30 to ground. Of course, it's pretty self-evident that if fuse 2 is good and the battery is charged and I've got good wiring, I'm going to have 30 and that test light is going to come on. Just as a reminder for all of you young and old timers, what's the first thing you do when you grab a test light? The very first thing you do. The answer is, of course, test the test light. Make sure that sucker works so that you don't make all these false opinions by a test light that doesn't work. Okay, now I have a test light to ground and I've touched pin 85 of this circuit. What will that test light do? The answer is nothing. If it comes on, you've got a short somewhere between B plus and that circuit on 85. Now, if you connect the test light to B plus, it should come on when you touch 85. If it does not, you have an open ground. Now, my advantage to suggest to you is on relay socket testing is instead of thinking that you've got an open ground and start peeling back harnesses and cutting tape and wire looms and all that, you can test for that right here before you even have surgery. It's a huge speed saver. Now I've got a test light connected to ground, touching terminal 87 of the relay socket. What will that test light do? The answer is nothing, unless there's a short somewhere to another B plus in that circuit. Now I'm going to connect my test light to B plus and touch 87. What will the test light do and what will happen? The answer is, depending on the resistance of the load, The test light will come on dim, and the load, depending on, it's got to be pretty low amperage like the bulb, it might come on dim or operate very poorly. Don't care. What it's telling me is I have a conductive path from B plus to the load. Now, if I wanted to eliminate any doubt, I would take a fused jumper wire, as I did before, from 30 to 87 and measure the amps. And again, a fused jumper wire between 30 and 87 will give us my circuit amperage, including the device, but all of the connectors, the grounds, the corrosion, the looseness, rust, whatever. Wait a minute, you don't have rust out on the West Coast. Sorry about that. Now we have a ground switched relay. The only difference is B plus from fuse 1 goes to 86, waiting for something to turn it to ground. And that is where the switch is. So now we put our test light to B plus. That test light will be off until somebody turns the relay on by closing that switch. Now, whatever is supposed to close that relay, it may not be a toggle switch. It may have to be something that you command either bidirectionally or somehow close the ground circuit of that relay. Now you're testing the control circuit of the relay. And again, the same thing will happen here on B plus to the load. The same thing that happened whether it's positive switched or ground switched. Makes no difference. And of course, just a reminder, when jumpering anything on a relay socket, always use fused jumper wires. Always add a careful visual inspection of one of the best diagnostic strategies. Inspect the terminals, inspect the socket, look for green, look for corrosion. It doesn't take much corrosion to cause circuit performance problems, because remember, we're dealing with milliamps here in the coil circuit. It doesn't take much to screw it up. Now, some schematic or some service information, GM especially, does not want you to wiggle relays. They don't want you to, as they say, waller out those connectors, those terminals. But I always do a little wiggle test to see if I have a loose connection. Swapping can be a good idea as long as you have identical relays and that the swapped one also works properly. I could tell you a story about a guy that did this and replaced a fuel pump, which means he had to drop the tank, take the fuel pump module out. It was about $300, put it back in, and it didn't work. Why didn't it work? Because the relay that he swapped was bad too. He felt a little bit embarrassed about that one. Remember, when swapping relays, you can use a 4-pin in place of a 5-pin if 87A isn't used. Specialized equipment. There is a proliferation of specialized equipment that you can get for testing relays and relay sockets. Lyle makes one that's very common. They take this adapter and you pull the relay out, plug the adapter in, and then put the relay in top. And that gives you test points for all of those 4 or 5 pins. Snap-on makes one, Mac makes one. There's all kinds of different specialized test equipment. I am not advocating which one to buy. I have one piece of relay circuit testing equipment, and I'll show it to you next. That's this one. That's called the AES Wave U Activate. It comes with a bunch of adapters for different size relays. It's got a current loop built into it, so all you do is put your inductive ammeter or your scope clamp over there, and it'll tell you which one is 85 or 86 is ground or positive. It tells you if 30 is B plus or the device. It's a pretty neat tool. Unfortunately, it's on US back order right now from AES Wave, It's a great tool. Again, I am not suggesting you buy one or the other. This is the only one that I have, and I don't believe in a lot of specialized test equipment because I like to make my own, but I couldn't make that. Again, always use fused jumper wires. And here is where I said, you want to fuse the jumper at about 75% of the normal circuit fuse rating. I knew I said that somewhere in there.
Dick, you're down to 15 minutes.
Yep. So, be honest now. Are you comfortable with your current knowledge of the operation, testing, and diagnosis of relays today? So did you learn something new that you didn't know prior to coming into this class? I hope the answer is yes. I hope that at age 75, I didn't drool too much and was able to communicate my ideas as succinctly as possible. I do appreciate all of your attention and your involvement. The handouts, both of them, the one that's currently available and the new one will be made available to you when I finish it. And again, thank you from the old man. I'm the senior member of this group, proud of it, 75 and still kicking. So thank you for your time, guys. And now if there's any questions or open discussion, I would entertain anything that you want to discuss. Sounds like I did a masterful job, huh?
What you can't hear, Dick, is the thundering applause.
If only that were true.
While we're waiting to see if anybody else wants to chime in with questions, there we go.
Yeah.
While we're waiting to see if anybody has any additional questions, and don't hesitate to interrupt me, guys, if you see one.
There is a question in there. They want to know, can you tell me where terminal 87A is connected and what is the function of that terminal?
On a circuit that has two circuits that wants to be controlled, one on, one off. And I may defer to Rick Martineau, who may give me a GM application to that, but a 5-pin relay, again, when the relay is not energized, the circuit connected to 87A would be on. And then when you energize the relay, you would disconnect that circuit and turn on the circuit connected to 87. Rick, you have an application for me on that?
A lot of the old GM fuel pump control relays actually help the fuel pump test lead to 87A.
Yep. The old, they had I think it was a green, maybe a gray connector sticking out under the hood that wasn't connected to anything. And that was a fuel pump relay connected to 87A. So you could put 12 volts to that connector and the fuel pump would run regardless if the key was on or off. A lot of techs use that to empty the gas tanks before they drop the tank, and et cetera, et cetera. Great, I'd forgotten about that.
And that's an example of when they use 30 as the output.
Yes, yeah, thanks, Rick, I appreciate that.
Freightliner truck also used them for high beam headlights.
You could use that as a dimmer switch. Absolutely could use it as a dimmer switch. 87A would go to the low beams, and when you want to control high beams, turn them on, you energize the relay and you go up to 87, turning the high beams on. Another great application. Thanks, Jeff.
There was another fuel pump on GM when they were using the resistor in series with the fuel pump on the first supercharged cars. So 87A through 30 would power the fuel pump when you were just driving down the road, and when you went into boost, it would switch back over to 87 and bypass the resistor as well.
Yep. Cool. Experience talking there.
Hey, Rick, wouldn't it be used maybe for like traction control too, or like if you turn it off, it turns the light on your dash to let you know that the traction control is disengaged?
There's all kinds of things like that out there. I mean, you just need to look at circuits. I've seen them used for daytime running lights as well, where they could use it to put the headlights in series and things like that. So there are lots of examples out there. It's just contacts that are closed with the relay not energized, and then the energized relay changes the state.
That's a great question. You do this for so long, you forget about some of those things that we used to deal with every day in the old days, but thanks for asking that. Anybody else? I hope that you've come away with a different way of looking at relay testing. To me, a lot of technicians are missing the boat when they just swap a relay and then say, well, does it work or not? I don't know. So these aren't complicated tests by any means. Don't require a lot of expensive equipment, but they're very valuable and very diagnostic in nature.
Yeah. Lots of great appreciation and good feedback in the Q&A here. Appreciate everybody who tuned in, and huge thanks to Dick Krieger for giving this presentation. Definitely living proof that you can teach an old dog new tricks, and he can even turn around and teach you. So thanks again for that. The only other question that I'm seeing here from a few of you, let me take one more glance here. There's a bunch of questions about where to get the handout from this, so I'll show you that real quick.
I will
Jake,
comment.
maybe do a screen share.
Yeah, can you see my screen now?
Yes.
Okay, so here we are, just at the ConsuLab homepage. You click under.
Nope, not there. Not there.
Sorry, right over
Virtual
here.
conference,
Virtual
yep.
conferences on the left.
Yep.
And you can find the Western Wheels Conference, and most of these are going to be. Most of the sessions are going to be right in here.
So if they click on that newest relay technologies.
And then the download section right here.
You do have to be logged in. So if you don't have a ConsuLab login, you have to set one up, and I'll be the one that approves it. And then you'll be able to download the presentation there. And Jake, if you go back one.
There is just one note. That is one extra step there to take, but it's well worth it. It does unlock quite a bit of good content here for you, and makes it easy for you to submit a wish list through ConsuLab.
If you scroll to the product page there for the virtual conference.
Down here?
Yep, click on that.
You got JB's in here, right?
JB's presentation is located right there. The one earlier today about the hidden funds. Again, you have to be logged in. It's a big file, so it will take a little time to download, but you can find that right there as well. Likewise, Al's that he made is also, if you go back one, it's listed under his DSO. I'm sorry, his CAN bus. Yeah, sorry. CAN bus is right there.
I just want to mention that if you go to, as you're being directed, you're going to download the original electrical diagnostic strategies handout, which is pretty valuable and good stuff, but the one that I'm yet to complete, the relay new technologies, will be in that same location when I finish it. I would also like to address another comment here that I see in Q&A. I lost his name now, but he said, I would suggest never using a test light to instead use a power probe and a schematic. I certainly do not disagree with his statement about power probe. Every class that I usually teach, I'm asked for my personal opinion on power probe, and I've seen power probe 3, power probe 4, power probe hook. They are a fantastic diagnostic tool. The only thing I object to, and it's my personal opinion, is they got a button that you apply B+ when you push the button, and it does not come with a brain card. And some students, if you just hand them a power probe and they go out and accidentally put it on the wrong spot and push that button, bad things can happen. Is it a great tool? Absolutely, it's a fantastic tool. And in the right hands with training and the right resources, it makes a great time-saving tool. Don't misunderstand my comments about power probe. Personally, I don't have one because I don't do this work every day anymore. And I find that a test light, the worst thing that can happen to you with a test light is the test light could come on if you shorted it out. That's why some people use the old seal beam headlight in a cardboard box when they're applying 12 volts to something. Because if they short it out, the worst thing that'll happen is the headlight will come on. So power probe is a great tool. and I just wanted to give you my opinion.
Good deal. Another question here regarding where to find stuff.
Mm-hmm.
I'm going to go right back to ConsuLab's website. They were asking about the webinars, where those are located. That one, that's where I almost clicked at the beginning there. If you click on resources at ConsuLab.com, it's going to be the first one right here, ConsuLab Distributed Learning Webinar Series. That'll take you to their YouTube page, which has all of those organized into a playlist here for you. As you can see, they did quite a few sessions there. We got 40 of them posted. So there's that. Go ahead.
Excuse me, Jake. The only caveat that I would say about that, and these are all good information, this has been almost a 2-hour class. Some of those are abbreviated because we were working within a tight timeline. Some were multiple sessions, part 1, part 2, part 3. But to have a bumper to bumper, you know, this is a full 2-hour class, and I guess you're recording this for later use, but those on the line were under a tighter timeline.
Thanks, Dick. One other thing I'll point you to, because there are a lot of resources and a lot of questions that you're going to come across. If you get stuck at any point, if you don't want to click through to find this stuff, you can just come to dactic.com, the contact page here, and email any one of us, and we'll make sure that you get what you're after. So